Hello everyone, I'm Cecelia and I'm going to present my final year project on human facial attribute editing using generative adversarial networks, GANs. In this video presentation, I will be discussing my research on designing and evaluating GAN-based model for facial attribute editing. Specifically, I will be addressing the following. First, I will introduce this project background, objective, and scope. Second, I will present the methodology and algorithm used in this project. Third, I will show and discuss the result of my experiments. Lastly, I will conclude all my work and discuss the possible future work. More examples will be displayed at the end of this presentation. GAN is composed of two neural networks, a generator and a discriminator. The generator can map random noise to realistic samples, while the discriminator is used to evaluate whether the generated samples are real or fake and provide feedback to the generator. Another important concept used in this project is global alignment. In this work, the global alignment algorithm I use is GAN, which can align the visual features of each image in a specific object dataset to a common center. Hence, we can further edit the aligned images and propagate the editing back to the original images through GAN. This project aims to develop a downstream applications of GAN, which involves human facial attribute editing on aligned images by training another generative model, ATT-GAN. Undoubtedly, those editing can be propagated back to the original images in the same pipeline. GAN is a GAN-supervised algorithm which uses a pre-trained style GAN tool to generate a training data pair. Theoretically, any pre-trained GAN can be used in GAN. However, to generate a training data pair which is same in object feature but different in pose, style GAN is the most reliable choice because of its powerful style mixing capability. The training data pair is used to train a spatial transformer network (STN) to execute the geometry transformation for the global alignment. The picture shows the structure of spatial transformer. However, GAN algorithm utilizes a composed of two spatial transformers, that is, a similarity spatial transformer and an unconstrained spatial transformer. The objective function of GAN is formulated as a perceptual loss between transformed images and generated label plus two regularizer which encourage the flow to be smooth and not to be deviated. The weighting coefficients are set as 2500 and 1 respectively. In this project, I use a relatively small generative model, ATT-GAN, for editing facial attribute. The training model of ATT-GAN is composed of three components: attribute classifier, which constrains the generated image to correlate on the desired attributes; adversarial learning, which ensures generated images visual reality; and reconstruction learning, which enables the decoder to restore the attribute excluding details. This slide shows the objective functions for training the ATT-GAN model. After GAN and ATT-GAN were trained separately, the pre-trained ATT-GAN was integrated into GAN algorithm, allowing for alignment, editing, and editing propagation to be performed in a single application. These are the environment settings for running the following experiment. The dataset used include Cecelia and Cecelia HQ. The pre-trained style GAN tool used in GAN is trained on Cecelia, while the ATT-GAN is trained on Cecelia HQ to avoid some undesired artifact. As mentioned before, the pre-trained style GAN tool used in GAN is trained on Cecelia. However, the well-trained GAN can also generalize to unseen human face images. The editing method suggested by the author of GAN is to add on some objects to the images as shown in the figure. Before that, those object images need to be prepared based on the average aligned face to ensure the correctness of propagation. However, this project tries to utilize a generative model to edit the facial attribute of the image. The facial attribute edited include browsy eyebrows, rosy cheeks, mouth slightly open, smiling, wearing lipstick, eyeglasses, moustache, and no breath. This is the result generated by a well-trained ATT-GAN. The ATT-GAN can also modify multiple attributes simultaneously. I also performed quantitative analysis by evaluating the facial attribute editing accuracy of the ATT-GAN. It achieved an average accuracy of 78.32% per attribute. This is the final result when the alignment, editing, and editing propagation are performed at a single pipeline. This algorithm can also work well on video frames. Lastly, I also evaluate the importance of global joint alignment by removing the unconstrained spatial transformer. As shown in the figure, the editing of 18 eyeglasses can perform properly by ATTGAN that was trained on the dataset pre-processed without T-flow. In conclusion, I developed a downstream application of angling by integrating the ATTGAN into the algorithm, which allows facial attribute alignment, editing, and editing propagation in the same timeline. In future, we can try to replace a suitable model for another facial attribute editing task, such as facial expressions modification.